Question is correct. Question 5 just asks, how do you find the pH at the equivalence point? So first I'll write down the definition of equivalence point. So this happens when the amount of titrant that is added is enough to completely neutralize the analyte solution. Okay, so I'm just going to give out an example. Of if you have a strong acid, let's call it HA, that completely dissociates into its ions H plus and A minus. If the concentration of HA was, let's say, 0.5, this is the initial concentration of our reactant, and initially we have a concentration of 0 for both of our products. The C means change. So during the reaction, there is going to be minus X change for the reactants as it is being turned to the products. So the change for the reactant is minus X, and for the products, it's plus X. Then lastly, at equilibrium, it's going to be 0.5 minus X, and X will be equal to the concentration of both of our products. So let's say there was a Ka value given. It's usually around like 4 point something times 10 to the negative 6, let's say. This Ka value is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA. So if we sub in our values from the ICE table, we can say 4.9 times 10 to the negative 6 is equal to x times x, which is x squared, divided by 0.5 minus x. So using a quadratic formula to solve for x, you end up getting a value equal to 1.56 times 10 to the negative 3, which is also equal to the concentration of H plus. So we want to know the concentration of H plus because in order to calculate for pH, it's going to be the negative log of the concentration of H plus. So for this example in particular, pH will be equal to negative log of 1.56 times 10 to the negative 3, which is equal to 2.81. Okay, so that's one way of doing it when you have a strong acid. And For the junior tutor's answer, they said to consider the titration of a weak acid by a base OH minus. So this requires a little more steps than just having a strong acid example. So they say to consider this titration. So this is the reaction where the weak acid plus OH minus makes A minus plus H2O. The ice table for Z moles HA titrated with X moles of OH minus is given below. Note that Z is equal to X. So here they have like a similar ice table. As seen in the table above, all of the HA and OH minus have reacted with each other to produce A minus and H2O. This means that the pH of the solution is only due to the hydrolysis of the conjugate base A minus. Hydrolysis of the conjugate base is shown in equation 2. So here they show A minus plus H2O makes OH minus plus HA. So it basically looks like the reverse reaction of the first one. The base dissociation constant expression for equation 2 is given below. So since this is our A minus dissociating to OH, instead of using a Ka expression, they use a Kb expression, which is equal to the concentration of OH minus times concentration of HA divided by the concentration of A minus. So here is the ice table for the hydrolysis shown in equation 2. So we substitute the equilibrium expressions into equation 3 and solve for X. Note that X is the concentration of OH minus and HA. Then we can get the pH in two ways. First, calculating the concentration of H plus using the auto-ionization of water. So this is another equation where Kw is equal to the concentration of H plus times the concentration of OH minus. And Kw has a value of 1 times 10 to the negative 14. Recall that the pH of solution is related to the H plus concentration through equation 5. So pH is equal to negative log of H plus. Another way to get the pH is by calculating the pOH and by using the relationship between pH and pOH. We calculate the pOH in the same way that we calculate pH. Then the equation that relates pH to pOH is obtained by getting the negative logarithm of equation 4. And you can double check your answer by seeing if pH plus the pOH is equal to 14. But basically this solution is correct.